Okay, let's continue our discussion of chemical equilibrium by talking about how to write equilibrium constant expressions. All right, so hopefully this won't be a very long video. I think this will be short-ish, but there are a bunch of little tiny topics that we need to talk about because in writing equilibrium constant expressions, the states of all of the reacting species matter. So we'll have to look at those independently. Okay. So first of all, we're going to look at the general form of the equilibrium constant expression. Then we'll look at equilibrium constants for soluble species. We'll look at activity, which is a new term. We'll define that, or sort of define that, later in the video. We'll talk about homogeneous and heterogeneous equilibria, and then we'll talk about equilibria involving gases or solids and liquids. All right, let's go ahead and jump into this. All right, so first of all, we can talk about the equilibrium constant expression. And one of the nice things about equilibrium, if you remember back to kinetics, we said when you see a balanced equation, you can't necessarily write a rate law for that reaction. In order to know the rate law, you have to do some experiments and take some data. Well, fortunately, that's not true for equilibrium expressions. Any equilibrium expression can be written directly from the balanced equation. And so if we have this balanced equation, for example, where A reacts with B to create C and D, those are the capital letters, and the small a, B, C, and D are the stoichiometric coefficients, then the equilibrium constant expression is just this fraction here. Okay, it is the concentration of both of the products, C and D, here in the numerator, divided by the concentration of the reactants here in the denominator, with both of those raised to powers equal to their stoichiometric coefficients. So if we've got A moles of A, then the concentration of A is raised to the power A. Okay, pretty much that simple. I want to add one little thing here. Textbooks don't always include this, and I don't always include this, but this ratio here, this fraction, this is true. The ratio of these concentrations reaches a constant once the reaction mixture has come to equilibrium. Okay? This is not necessarily true. In fact, generally it's not true throughout the course of the reaction, but only after the reaction reaches equilibrium. So technically, when we're writing this, we should include a little subscript EQ with all of these things, meaning the equilibrium concentrations. People often leave that off, and one, I won't penalize you for leaving it off, and to be honest, I'll probably leave it off myself a lot of the times. Oh, okay. I accidentally advanced a little bit too quick to the next slide. But basically, to summarize that, I just had a little bit of text at the bottom. You should be able to write that equilibrium constant expression, which is the concentrations of the reactants divided by the products, but you should also be able to state that in words. And I think in general it's really helpful to not just memorize mathematical equations, but to be able to say them in words and describe what they mean. And so what we had at the bottom of that last screen was just the equilibrium constant expression is the concentrations of the products divided by the concentrations of the reactants, each raised to the power of their stoichiometric coefficients. All right. So That actually brings us to our next slide. So the definition of our equilibrium constant expression is the concentration of the products that A plus B goes to C plus D, that reaction. Okay. This is how we are defining the equilibrium constant expression. Excuse me. And again, this is only true for the equilibrium concentrations. This is how we're defining it. If I ask you to write an equilibrium constant expression, this is what I want you to write. If anything in the textbook asks you to write an equilibrium constant expression, this is what they want you to write. Okay. However, the true definition is actually slightly different than that. The true definition is this same ratio, but it's the activity of the products divided by the activity of the reactants. Okay, so this is the activity of species A, this is the activity of species B. Again, if I ask you to write equilibrium constant expression, what I really want is for you to give this one. I'm only mentioning activity here because we need to do things a little bit differently for liquids and solids and gases and soluble species. They're all handled slightly differently, and the reason that they're handled differently has to do with this definition of activity. And so I'd like to include a short discussion of activity so that you can see where those different the different way that we handle these different species, so you can see where that comes from. Other than that, I won't really ask you much about activity. All right, so what is activity? Activity is actually a fairly complicated topic, and it's something that you'll study if you take upper level chemistry courses. You'll study activity in PChem and maybe in analytical chemistry briefly. And the topic is actually fairly complicated, but we can give kind of a simple definition. This isn't exactly correct, but it's pretty close. So the activity of species X is the concentration of species X divided by the concentration of species X in its standard state. And where the complication arises is that different kinds of species have different standard states. Okay, so the first thing we're going to look at are soluble species. Or let's say, I think soluble works fine, but dissolved is probably better. So if you have sodium chloride dissolved in water, and you're talking about the concentration of sodium or chloride, then that's an example of a soluble species. Anything anything that you would write with an AQ, anything in the chemical equation that has an AQ on it. Okay, so for dissolved species, the standard state concentration is 1 molar. Okay, and because the standard state concentration is 1 molar, when you are doing the activity, you put in the concentration of X, whatever that thing is, you divide by the standard state concentration, which is 1 molar. So basically what you end up doing is, all this does is it factors out the units. So the activity of a dissolved species is just the concentration in molarity, but written without units. Okay? All right. All right. So for dissolved species, the activity is just the concentration and molarity, but written without units. All right. Let's take a look at an example and see how that plays out. Okay, so here's a typical example. In water, nitrous acid dissociates into hydrogen ions and nitrite ions according to the following equation. And then it gives you an equation, a balanced equation. And the problem says, in one solution of nitrous acid, the following species concentrations were observed at equilibrium. Nitrous acid was 0.0035 molar, hydrogen ions 0.0016 molar, and nitrite ions 0.0016 molar. And here's the question. Actually, it's two questions. Based on these data, write the equilibrium constant expression for this reaction and calculate the value of the equilibrium constant. All right. So one thing I want to mention before we start is that there are two questions here, and I want to distinguish between these two, because you'll see both of these on quizzes and exams. The first one is write the equilibrium constant expression for this reaction. When you see that, that means write that fraction with the products divided by the reactants. Okay, that's what the equilibrium constant expression means. The second part is calculate the value of the equilibrium constant. Okay, calculate the value of the equilibrium constant means calculate the actual numerical value of KEQ. Okay, in order to do the first part, the equilibrium constant expression, all you need is the balanced equation. To do the second part, you have to have data. Okay, so that's one way. That's kind of a clue as to what's being asked of you if you're looking at one of these questions and you're not quite sure. All right, so for the first part of this, write the equilibrium constant expression. We would just write this like this. KEQ is equal to concentration of the products, hydrogen ions, and the concentration of the nitrite ions divided by the concentration of the reactant, which in this case is nitrous acid. And then we would raise all of these to exponents equal to their stoichiometric coefficients. But in this balanced equation, all of those stoichiometric coefficients are 1, right? So they're all just raised to the first power. All right, the second part of the problem says calculate the value for the equilibrium constant. Okay? And this is where that the activity has a small role. Okay, when we're putting these in, we're going to put in for here. We're going to put in the concentration of hydrogen ions in molarity, but put it in without units. Okay, so the concentration is 0.0016 molar. We're going to put it in there, but leave out the molarity. All right, then next is concentration of nitrite ions, which is here, also 0.0016. Okay, oops, left out a 0.0016. It's important that the concentration is in molarity. You won't get the right answer if it's not in molarity. Okay, although we're going to leave the units off. And in the denominator, concentration of nitrous acid, oops, I just started writing, I'm like, something looks wrong here. Okay, sorry about that. Concentration of nitrous acid, which is 0.0035. And then we just plug all of that into our calculator. And when you do that, I think we get 7.4, excuse me, 7.3 times 10 to the minus 4. Okay, and again, because there are no units here, there are no units here. Okay, I often say that it's extremely important to include units in all of your calculations, and generally speaking, it is. But when you're calculating an equilibrium constant, that is a unitless number. Okay. All right. Let's go and look at. Let's do a couple of quick practice problems. All right, here are three quick practice problems. To save space, I didn't write this on the page, but the problem for each one of these is just write the equilibrium constant expression. I didn't give you any data with which you could calculate the numerical value of the equilibrium constant, so just write the equilibrium constant expression. For example, for this first one, since it's very simple, just like the last one, concentration of hydrogen ions times concentration of fluoride ions divided by the concentration of HF. And again, technically these are all equilibrium concentrations, but people often leave that off, and frankly I leave it off. I certainly won't hold it against you if you leave it off. It's better if it's in there. Okay, take a minute, pause the video, and do the same thing for the next two. Okay, and then when you're done, unpause it, and we'll compare our results. Okay, for the second one, the product in this case looks a little bit unusual. This is a silver amine complex. Silver and ammonia with a net positive charge. But you can see here that's a dissolved species, so we'll just put that in brackets. Again, that would be concentration in molarity, but without units. And in the denominator, I have a concentration of silver and the concentration of ammonia. Okay. What's different here is we finally have a stoichiometric coefficient that's not a 1. So since there are 2 moles of ammonia, we need to raise that one to the second power. Okay. And for the last one, you should have concentration of hydrogen ions, concentration of sulfide, divided by the concentration of H2S, and again, this time it's in the numerator, a 2 there with the hydrogen ions. All right? Okay. Pretty simple, pretty simple. All right. So now let's look at gases. And again, I'm going to go back to the fact that technically what you put into the equilibrium constants are activities, and activity of species X for gases is the partial pressure of X divided by the partial pressure of X in its standard state. Okay. And for gases, the standard state partial pressure is 1 atmosphere. Okay. And so that means that for gases, what you're going to enter into the equilibrium constant expression is the partial pressure of that gas phase species divided by 1 atmosphere. And what this does is essentially the exact same thing it did for soluble species, right? For soluble species, you put in the concentration and molarity, but the units canceled out because this thing at the bottom was 1 molar. For gases, you do the exact same thing. You put in the partial pressure in atmospheres, but the units cancel out because you've got 1 atmosphere in the denominator. Okay? So, I don't think I've ever seen a problem in a textbook where they give you the gas pressures in torr. But they could, I guess. And I haven't done that to anyone. But if they did, it's important to change the pressure to atmospheres. And again, but when you plug it into that equilibrium constant expression, you don't include the units, so the calculated equilibrium constant ends up being unitless, just as it was, well, as it will be for all of them. For all equilibrium constants are unitless. Okay. So we'll do a couple practice problems for gases. I'll do the first one to show you what I'm looking for. To write the equilibrium constant for this reaction, this is 3 moles of oxygen converting to 2 moles of ozone. So the equilibrium constant is just going to be, in this case, the partial pressure of the product. So that's the partial pressure of ozone divided by the partial pressure of oxygen, the reactant, and then each one of them raised to a power equal to their stoichiometric coefficients. So for the ozone, we need a 2 up here, and for the oxygen, a 3. Okay. Go ahead and pause the video, write the equilibrium constant expressions for the next two reactions, and then unpause and compare your results with mine. We'll see how we did. All right, so the equilibrium constant is just the products divided by the reactants. Because these are gases, we're going to write them as partial pressures. and then we need to raise them to the power of their stoichiometric coefficient. So we put a 2 there on the NO. And for the last one, we'll have the partial pressure of ammonia raised to the second power divided by the partial pressure of nitrogen times the partial pressure of hydrogen raised to the third power. All right, pretty simple. And then if you're doing calculations, you need to make sure they're in atmospheres, but put them in without units. All right. Okay. I just want to mention a definition here. We can talk about homogeneous equilibria and heterogeneous equilibria. And definitions are simple. You may have already guessed them, actually. Let's see. Homogeneous equilibrium just means that all of the species are in the same phase, right? So this is something like this reaction we had here, HF. When you form hydrogen ions and fluoride ions. Everything is aqueous, right? Or one of the gas problems we just had on the last page. All of the species were gases. So those are homogeneous. Okay? Heterogeneous, of course, means that you have a mixture of phases. So you might have aqueous species and gaseous species. You might have solids and gases, or dissolved species and solids, any kind of a combination. That would be an example of heterogeneous equilibrium. All right? When you've got heterogeneous equilibrium, all you do is combine the rules that we had before for each of the different species. Okay. So, for example, here's a really, really simple one. We've just got oxygen and oxygen. Hardly even looks like a reaction, but this one is in the gas phase and this is in aqueous phase. So this is a reaction showing gas phase oxygen dissolving into water. Right? This would be important, for example, in stream chemistry, particularly biology and things like that. You have to get oxygen dissolved in the water so that the fish don't die, right? The fish have to breathe. If we've got a reaction like this and we're writing our equilibrium constant expression, again, as always, it's just the products divided by the reactants. Our product is soluble oxygen. So that's O2, molar concentration of O2 in the solution. And our reactant is gas phase O2. So for that, we would put the partial pressure of oxygen. All right. Go ahead and write equilibrium constant expressions for the other two, and then we'll compare our results. All right. So for the second equation, it is, again, concentrations of reactants divided by concentrations, concentrations of products divided by concentrations of reactants, except that ammonia in this case is a gas. So instead of the molar concentration, we put in the partial pressure. Okay? And all of these stoichiometric coefficients are 1s. So everything is just raised to the first power. Let's see if it gets more interesting on the last one. All right. We got our products, which is hydrogen carbonate ions. That's a soluble species. So we'll use molar concentration. And on the left side for our reactants, we've got CO2, which is a gas. So we'll use partial pressure of CO2. and we've got hydroxide ions, soluble, so we'll use molar concentration there, and we've got 2 stoichiometric coefficients. So we need a 2 there and a 2 there. All right. You know what? Yeah, we need a 2 there, but I want to go ahead and fix this. Anybody see a problem? When I typed this in, I'm not sure what I was thinking. This is not balanced. All right. If you wrote it as I just did, you wrote it correctly, so good for you. But if you were paying extra close attention, you might have realized that should have been a 1. I had that was not balanced correctly. Okay, so with a 1, the equilibrium constant expression should look like this. All right, lovely. All right, let's go on to solids. All right, so we'll start with the definition of activity. Activity of species X, concentration of X, divided by the standard state concentration of X, and so for solids, the standard state concentration is just the concentration of the pure solid. Okay, so as long as the solid in your reaction is a pure solid, then this and this are going to be equal, and so for pure solids, the activity is just 1. Okay. Most textbooks will mention this and they'll use the phrase pure solids, but they don't usually say what that means. What that means, for example, is if you have something in your reaction, if you have, for example, copper, that would be a pure solid, right? And so when you enter that into the equilibrium constant expression, you would just put a 1 in there. But if you had brass, which is an alloy made of a mixture of copper and zinc, that would not be a pure solid. So if you had brass that was 50% copper and 50% zinc, that would not be a pure solid, and you'd have to determine what the actual activity of the copper was. I've never given problems like that. I've never seen problems like that in textbooks. Generally speaking, the problems, when they use solids, they're always assumed to be pure solids. So when you see solids in your reactions, you just put in a 1. Okay, so let's see what that looks like. All right, so here are a couple of chemical equations. We're going to write equilibrium constant expressions for these. I'll do the first one, and I'm actually going to do this in a couple of steps. You don't have to do this, but I would say I would recommend doing this. When you're writing the equilibrium constant expression, I usually put the solid in just to help me keep track of what I'm doing. And that it's particularly useful when you've got when one of the sides, either the reactant or the product, is only a solid. And so a 1 is the only thing in the numerator or the only thing in the denominator. It's especially helpful in those cases. But anyway, let me go ahead and show you how I would do this one. For this first one, have the concentration of iron in the numerator and the concentration of hydroxide in the numerator. There are 3 of these. So we're going to cube that, and in the denominator we have, we have the concentration of iron hydroxide. Okay, but because the iron hydroxide is a solid, this whole thing becomes a 1, and so this ends up giving us concentration of iron ions times concentration of hydroxide ions cubed divided by 1. And so the equilibrium concentration is just concentration of iron 3 ions times the concentration of hydroxide ions cubed. Let me write this here, hopefully a little bit neater. Believe it or not, I'm trying to be thoughtful with my handwriting. Trouble is, when I write very clearly, I write slowly, and so I'm worried about making the video way too long and making you all very, very bored as I write slowly and clearly. Anyway, so this is what our equilibrium constant would look like for this first one. The iron hydroxide has basically just disappeared because when you put a 1 into a fraction, that 1 just disappears. Okay. All right. Go ahead and do the next two, and then I'll do them. I'm going to write them down at the bottom to work them out and put the answers in. But you go ahead and do them first, and then pause the video, work through them, and then unpause, and we'll compare our results. All right, so for the second one, again, I'm going to start by including everything. We've got silver bromide as a product. And our reactants are silver ions and bromide ions. Okay. But because this is a solid, this whole thing in the numerator equals 1. Okay. And this is one of the reasons that I think it's helpful to write all of this out, because when you've got a 1 in the numerator, unlike the last case where the 1 was in the denominator, let me write this. 3 over 1 is just equal to 3. You can just ignore this 1, right? But if you have 1 over 3, you can't ignore the 1. You have to keep that the 1 in the numerator. Okay, so that's why it's helpful. This is the place where people most often make mistakes with solids, is when they put in a 1, they lose kind of the shape of the fraction. They lose the distinction between the numerator and the denominator. All right, so when that solid turns into a 1, we end up with in this case the reciprocal of the silver concentration times the bromide concentration. Okay. All right, and then let's do the last one. The last one looks a little bit more complicated. We've got copper 2 ions and so we've got a gas here. So we've got the partial pressure of hydrogen sulfide, and in the denominator we've got copper sulfide and the hydrogen ions. Because of this coefficient, we have to square this, and because the copper sulfide is a solid, that just becomes a 1. And so what we're left with is our equilibrium constant expression. Concentration of copper 2 times the partial pressure of hydrogen sulfide divided by concentration of hydrogen ions squared. Okay. All right. Okay, now for liquids. Liquids, you'll be happy to know this is really easy. For liquids, it's just like it was for solids. Okay, so the standard state concentration of a liquid is just the concentration of that pure liquid. So as long as any liquids in your chemical equation are pure liquids, then this whole thing is just going to be a 1, exactly as it was for solids. Okay. And again, the meaning of this phrase pure liquid is if you've got a reaction taking place in water, and water is one of the reactants, well, that solution is going to be almost entirely water, right? So it's essentially pure water. But if you're doing the same reaction in a solution that was 50% water, 50% ethanol, then that would not be considered a pure liquid, and you would not put a 1 there. You'd have to do something else. Okay. But again, just like with solids, everything I've ever seen in the textbooks and anything I've ever put on a quiz before always includes the assumption that all of the liquids are pure liquids. So we'll just put in 1s for all of those. All right. So here are 3 problems. Go ahead and hit pause. You've got the hang of this. So go ahead and hit pause and work through these, write your equilibrium constant expressions, and then I will do the same and we can compare our results. All right. So for the first one, on the product side, we've got the concentration of iron 3 ions and the concentration of hydroxide ions. Excuse me, that's not right. Times the concentration of water. Times the concentration of water raised to the 3rd power. And on the reactant side, we've got concentration of iron hydroxide and the concentration of hydrogen ions raised to the 3rd power. Okay. So now this is a heterogeneous reaction, and because water is a liquid, and this is, all of these say aqueous, meaning this reaction is taking place in water. So that means it's essentially in pure water. So this whole thing is going to become a 1, and this is a solid. So this whole thing is going to become a 1. And so what that leaves us with is just the concentration of iron 3 ions divided by the concentration of hydrogen ions raised to the third power. Okay. All right. Let's take a look at the second one. On the product side, we got the concentration of water again, and the concentration of fluoride ions. On the reactant side, we've got hydrofluoric acid and hydroxide ions. Well, this one looks pretty simple. All of our stoichiometric coefficients are 1, so we don't need to worry about that. And everything is aqueous with the exception of the water. That's going to turn into a 1. And so we're just going to get concentration of fluoride divided by the concentration of HF times the concentration of hydroxide ions. Alright, and then this last one looks kind of complicated. Let's see what happens here. On the product side, we've got calcium ions, and we've got water, and we've got CO2. Now this is a gas, so we're going to put in partial pressure of CO2. And on the reactant side, we've got calcium carbonate, and hydrogen ions. We need to raise hydrogen ions to the second power. All right. Now, the water is a liquid. It's a pure liquid, so that's just going to be a 1. The calcium carbonate is a solid. We'll assume it's pure solid, so that's going to be a 1. So that leaves us with the equilibrium constant is equal to concentration of calcium ions times the partial pressure of CO2 divided by concentration of hydrogen ions squared. All right. Fantastic. All right. So, a lot of little bits in this one, but all of them are pretty simple. So, we end up with summary. Remember the general form of the equilibrium constant. Again, even though it's actually defined in terms of activities, if I ask you for the equilibrium constant, it's just the concentration of the products. This goes for that hypothetical equation that I showed you earlier, divided by the concentration of the reactants, all of them raised to the power of their stoichiometric coefficients. And technically, this is only true at equilibrium, so this should be equilibrium concentrations. But a lot of people leave those off, and I won't penalize you if you leave that off. If you put it in there, it'll make me smile, but I won't penalize you if you leave it off. All right, so based on the definition of activity, what we found is that when you're putting these putting things into this equilibrium expression for soluble species, generally anything that says aqueous in the equation, you would just include that species as its molar concentration but written without units. For gas species, same thing. You put in the partial pressure in atmospheres, but you would write it without units. And for pure solids and liquids, for both of those, you would just put in a 1. And since it's a fraction, putting in a 1 generally means you just leave it out entirely. But I would encourage you to put it in as you're working your way through, because if the 1 is the only thing in the numerator, you can't quite leave it out. You have to include the 1 in that case. So do that thoughtfully. Okay, I think that's really it for this one. Thanks, everybody. I enjoyed going through this with you. I hope you enjoyed it. I was going to say I hope you enjoyed it as much as I did, but really, if you enjoyed it half as much as I did, I would be satisfied with that because I enjoy this. And I know not everyone does. But all the best, and I will see you with the next one.